Hello, my name is Yuvin Indipagunwardana, and I'll be talking about a video project that I did for the structural analysis subject. And in this video project, I'll be talking about a particular structure that I've chosen and how I analyzed it and the calculations that I did in order to analyze it. So, this is the structure that I've chosen. It is a storage steel shed which is 1.5 meters in width, 1.5 meters in length, and 1.77 meters in height. It is also located in my own backyard, which is one of the reasons why I have chosen it. And I started off with finding the reaction forces of the beam element, which I chose as the roof structure of the roof section of the structure, and I wrote a free body force diagram including the forces, the reaction forces, which is Ax, Ay, and By, and also the distributed load 6.66 kilometer per meter on the left hand side and to zero to the right hand side. And so I did some calculations and found out that the reaction forces By is equal to 1.998 kilonewtons, Ay is 2.997 kilonewtons, and Ax is 0. So, move, sorry. Moving on, I then found the function of the overall point load and also the function of the line of action, the distance of the line of action of the this overall point load from the right end of the beam. And thereafter, I use this in order to find the shear force and bending moment functions, which are for two separate ranges. So these two right here for the range 0 to 0.25 meters, and these two right here are for the range of 0.25 to 1.5 meters. And next, using these functions, I was able to construct the shear force diagram, which is right here, and also the bending moment diagram, which is right here. And also using these graphs, I was able to find the maximum shear force 2.997 kilonewtons and the maximum bending moment 0.76415 kilonewton meters. Thereafter, I calculated the and derived the functions of the slope and deflection equations. At first, I did for the range of 0.25 to 1.5 meters. So I used integration of the bending moment function and found out first the slope and thereafter the deflection equation. But these equations have the constants in them, so I had to constant C1 and C2 in them, so I had to take the boundary conditions and found out the values of C1, which is this, and for C2, which is this. And thereafter, I obtained the complete function of the slope and deflection equation for that particular range. Thereafter, using the deflection equation, I found out the maximum deflection in the range of in this range, and I and I found out the function EIV max is equal to this number right here. And thereafter, I took the value of E, which is the Gaussian modulus, which has 210 GPa, which is the because the beam is made out of steel.
You wanna get one of the Lion King versions?
And also the moment of inertia, which is this number right here. Thereafter, I found out the maximum deflection is this number right here. Also, I found out the same. I did the same method and found out the slope and deflection equations for the range 0.25 to 0 to 0.25 meters. It's this same integration and also the finding of the constants using the boundary conditions. Thereafter, I found the maximum bending stress of the beam using this equation here. I used the maximum bending moment I found using the bending moment diagram and also the moment of inertia to find this answer, which is the maximum bending stress. Thereafter, I use the values of the maximum shear force, which is this, the partial cross-section area, which is the area of the shaded region right here, and the distance y of the centroid of the shaded area from the neutral axis, which is this line in the middle, and the moment of inertia value, and also the width of the cut, which is 1.5 meters, which is this distance right here. And using these values, I found out the maximum shear stress, which is this value right here. And thereafter, I found the maximum principal stresses, which are sigma 1 and sigma 2. And the sigma 1, as it turns out, was equal to the maximum bending stress, and sigma 2 is 0. And also, I found the failure planes caused due to this maximum principal stresses, which is 0 and 90 degrees. Next, I calculated the maximum in-plane shear stress, which turned out to be equal to the maximum shear stress. And also, the failure planes of the maximum in-plane shear stress is also the same as that of the maximum principal stresses, which is 0 and 90 degrees. So these are all the calculations that I did from a radio project, and so thank you for watching.